Continuing on in our electrolytic cells series, we want to look at stoichiometric calculations for electrolytic cells, and you'll see as we go along how stoichiometry applies to these reactions. So welcome, and let's go. Let's examine first the electrolysis of melted NaCl. The more intelligent way of saying that is molten NaCl. The power source provides electrons to the cathode, which attracts sodium ions to become sodium metal. Simultaneously, the power source pulls from the anode electrons that chloride ions release as chlorine gas is formed. So look at this carefully. You may want to pause the podcast and just read this a couple of times, because you need to know how the power cell relates to the cathode and the anode. And this is a simple explanation, but I think one that will ring true. We're looking at the relationship between charge and our product. And so Faraday's law of electrolysis says this: the amount of each substance produced at each electrode is directly proportional to the quantity of charge flowing through the cell. And Faraday's law can be applied stoichiometrically. That's what we're going to do. Let's look at quantifying the amounts in a reaction as a result of electrolysis. The steps are real simple, but there are a lot of them. So pay careful attention. One of the first steps is you want to balance the half reactions to find the number of moles of electrons needed per mole of product. Once you've done that, you can use Faraday's constant, which is 96,500 coulombs per mole of electrons, to find the corresponding charge. Now, it's important that you know that Faraday's constant can be used as a conversion factor. When it's convenient, when we want to find charge, we'll have it set up as 96,500 coulombs per mole of electron. But if we know the amount of charge and want to find how many moles of electrons are associated with that charge, we can turn this constant upside down and have 1 mole of electrons over 96,500 coulombs. And then we'll use molar mass to find the charge needed for a given mass of the product. We also want to be able to relate current to charge, and the reason for that is current is easily measurable. Charge is not so easily measurable in a direct way. So current is measured in a unit called the ampere, and what an ampere is 1 coulomb flowing through a conductor in 1 second. So we can set this up as 1 amp is equal to 1 coulomb per second. If we know the current associated with an electrolytic reaction, and we know the amount of time over which the reaction is occurring, that current is applied, we can find the total amount of charge in coulombs. The way that we do that is we take the current times the time in seconds. Since an ampere is a coulomb per second, when we multiply that by a second, the seconds cancel, and we're left with the magnitude of coulombs as our end result here. So this is how you find the amount of charge. You take the current and multiply it by the time. Now, another thing to remember is that coulombs per seconds can also be looked at as a conversion factor, and sometimes we want to find the amount of time when we know the charge, and so we can also multiply by the coulombs per second turned upside down so that our coulombs cancel and we're left with time rather than charge, depending on what units we begin with. We're going to do a series of sample problems. The first one will involve a metallurgist. That's somebody who is an expert in metals, and this particular individual is plating an object with 0.85 grams of chromium, which is obtained from an electrolytic bath containing chromium 3 sulfate. The chromium is 3 plus in charge, the sulfate is 2 negative in charge, so the ratio of ions is Cr2, SO4 in parentheses 3. We want to calculate what current is required to finish the process in 6 minutes. We want to go through this step by step, And so we're going to do the steps one at a time. These steps can actually all be combined in one long stoichiometric equation, but I think it's easier to teach and easier to learn if you see them one at a time. What we want to do first is to write the half reaction that represents the reduction of the chromium-3 ion. So we have Cr3 plus 3 electrons is Cr. Next, we determine the amount in moles of electrons transferred for the 0.85 grams of chromium. If you're wondering why it's important to know how many electrons are involved in the reduction of chromium, it's because there's going to be 3 moles of electrons for every mole of chromium. So we're going to use a stoichiometric equation, take our 0.85 grams of chromium, and first change it to moles. So we multiply that by a conversion factor of 1 mole of chromium over 52 grams, and then we can find the total number of electrons by multiplying by the conversion factor 3 moles of electrons for every 1 mole of chromium. And we got that 3 moles of electrons from the half reaction that shows the reduction of chromium-3 plus. Once we have the number of moles of electrons, we can calculate the charge in coulombs. So we know that there are 96,500 coulombs per mole of electrons. That's Faraday's constant. So we're going to take our 0.049 moles of electrons that are going to reduce the 0.85 grams of chromium and multiply it times Faraday's constant, our 96,500 coulombs over 1 mole of electrons. And when we do that, we get a total charge of 4.7 times 10 to the third coulombs. Now that we have the total amount of charge that's involved in this electrolytic process, we can calculate the current in coulombs per second, which is an ampere. So we're going to take our 4.7 times 10 to the third coulombs that's delivered over a 6-minute period, and we're going to multiply that times 1 minute over 60 seconds so that we can get coulombs per second, which is an amp. And when we do that, we get 13 coulombs per second, or 13 amps, as the current needed to plate 0.85 grams of chromium on this object in a 6-minute period. In the previous problem, we solved for the magnitude of the current that would be required to plate 0.85 grams of chromium onto an object in a 6-minute period. For the second problem, since you have some experience with how we do this, I want you to pause the podcast, write this problem down, and then see if you can solve it on your own. And when you're ready to check your answer, just resume the podcast and we'll see how you did. Now, sample problem 2 is this. How many seconds does it take to deposit 118 grams of zinc on an object when 2.30 amps of current is passed through a zinc sulfate solution? So go ahead and pause the podcast, try and solve it, and let's see how you do. Welcome back. Let's see how you did. First thing that you wanted to do here was, of course, to write the balanced half reaction for the reduction of zinc. And so it's zinc 2 plus 2 electrons will yield zinc solid. Next, since we know the mass of zinc that we're going to plate onto this object, we're going to find the moles of electrons associated with that mass of zinc. So we just stoichiometrically take our 118 grams of zinc, multiply it times the equality or conversion factor of 1 mole of zinc over 65.39 grams of zinc. When we do that, we'll have moles of zinc, and then we just multiply it times the equality or conversion factor that there are 2 moles of electrons for every mole of zinc. When we do that, what we'll find is that we need 3.61 moles of electrons in order to plate or reduce 118 grams of zinc 2 plus. Now that we have the number of moles of electrons, we can determine the charge associated with the 3.61 moles of electrons. So we take our 3.61 moles of electrons, we're going to multiply it times Faraday's constant, which relates that there are 96,500 coulombs of charge carried by every 1 mole of electrons. When we do that, we get a total charge in this reaction of 3.48 times 10 to the fifth coulombs. And finally, we've arrived to where we can go ahead and calculate how much time this is going to take. It's really important here that we use the relationship of amps to its more base units of coulombs per second. We know that we have a current of 2.3 amps, and 2.3 amps is equal to 2.3 coulombs per second. In order to find the total time, I have the total charge. What I want to do is take the 2.3 coulombs per second and flip it upside down and use it as a conversion factor so that I can cancel the amount of charge and be left with my time in seconds. So that's the setup that you see here. 3.48 times 10 to the fifth coulombs times the equality that in 1 second 2.3 coulombs are going to flow. And what we get is 1.51 times 10 to the fifth seconds. That may not sound like a lot, but to give you perspective, I went ahead and converted that to hours. If you're using a current as small as 2.3 amps in this reaction, it's going to take 42 hours. So that's the problem. How'd you do? Well, we've come to the end of part 2 of the electrolytic cell video podcast here at Ontario High School. There's one more part. It's a little bit shorter, but just one more sample problem that I want to take you through. And I want to leave you with a quote from the great British statesman Benjamin Disraeli. Despair is the conclusion of fools. I wish you well.